Components of the system that we're using here today are the DC motor from Quanser, and essentially I have two signals coming in and out of this DC motor. I've got one which is my command signal, it's an analog voltage, and then I have a tachometer, also another analog output voltage, and I'm going to interface those to my PC through this interface board, which essentially just breaks out all of the lines available here on my National Instruments data acquisition board. So I'll plug that into my laptop and be then commanding and driving all of that from my software here on the PC. The tachometer, as I spin the motor, essentially will output a voltage that's proportional to the speed of the shaft. And the input voltage that I have in, again, is coming through basically a power amplifier, and that controls the speed of the motor proportionally to the value of the voltage coming in. So this particular data acquisition card has analog input, analog output, counter timers, and digital lines. The analog input and the analog output are both 12-bit. 500 kilosample is the maximum sampling rate. And in this case, we'll essentially be using one analog input to read the response of the motor and one analog output to control the motor. My PCMCIA DAT card will connect directly into my laptop through a PCMCIA slot that I have here on my laptop. So this part of the demonstration, we're going to talk about the system identification of the DC motor. So in this case, we're going to do that experimentally. And so the setup here is I have my software ready to run, and essentially the software is going to send an analog output voltage to the DC motor, which will be a square wave, so essentially a step response, and then we'll read back the tachometer signal to get the response of the DC motor from that. And then from the stimulus and response data that we have received then through our software, we can actually get a transfer function for the DC motor. So we'll go ahead and run the software, and here you can basically see the motor going back and forth according to the square wave. From the plots here we can see our two signals. The white signal is the actual command signal that we sent to the motor, and then the red is the actual response signal then that we read back from the DC motor tachometer output. Okay, so here we're showing the system identification software, which will allow us to create a model for our DC motor. So it takes the incoming step response signal and allows us to vary the type of estimation that we're going to use. We can change the different orders for the coefficients, and the result of this process, of course, is an actual transfer function that we can use to model that system. The next step is to do the control design. Now what you can see here in the software is the actual transfer function model that I have obtained from my system identification. The graph that I'm showing you here is the step response of the controller, and in this case the controller is a PID controller. If I go ahead and select the derivative here, you can see the corresponding change in the step response of the model. This allows us to adjust the proportional, integral, and derivative gains to obtain the response that we want from the system. So here you can see the LabVIEW block diagram of the simulation. So now that we've got a model for our plant and we've finished our control design, we'll actually want to implement that here in simulation so we can see the response to an incoming signal. So what we see on the block diagram is we have the model of our controller, so that's what we would have designed maybe with our PID software. We have the plant model here, which is the model of the DC motor. And essentially what we're going to do is we're going to generate a signal from LabVIEW and insert it into that system and see how it responds. And this would give us a good idea of what it would look like if we were actually controlling the motor. So this is the front panel of the LabVIEW diagram that we just saw. And essentially what it's doing is simulating the response of the DC motor to a square wave or a step input. On the left we can change the amplitude of our signal there. We could change the frequency of the signal. And we could also change it to a different signal type to make sure that our controller is responding the way that we want to. Now the next step then is to actually implement the control through hardware. So you'll see I essentially have the same diagram. I still have my controller model shown here, but you'll see I no longer have a plant model. In essence, the model or the transfer function I was using before is now going to be replaced with the actual DC motor. So in this case I have an input signal coming in here, so I'll read what the DC motor is doing. I'll send it through my control loop, and then I'll output the correct voltage then to keep it at the speed that I want. Okay, so this shows the actual front panel of us implementing the system now. And what we're doing here is we're actually commanding the motor to vary its speed sinusoidally, and then we're reading back the response of that motor. So you can see the two different signals, the white being the command and the red being the response, showing that our controller's doing a pretty good job of keeping up with the sinusoidal speed.